Welcome to this lesson on one of the four types of integrated reasoning questions you'll encounter on the GMAT, graphics interpretation. So let's begin just by talking about the logistics of this question type in the integrated reasoning section. First, you'll want to assume that there will be 3 to 4 questions of graphics interpretation per 12 question integrated reasoning section. It's just kind of an average that you'll see. You'll expect a single slide that is going to contain a figure that you will need to interpret. And you're going to have 2 to 3 questions for these slides, and you have to get each correct in order to get credit for that slide. You don't get partial credit for graphics interpretation questions on the integrated reasoning. So let's talk about strategy here. First, assume that you're going to want to spend about 2 minutes per question for these graphics interpretation slides, and you're going to have a maximum of 3 minutes for any graphics interpretation slide. These are generally going to be a little bit easier, so you want to allocate less time as you engage with them. You're going to have to read and interpret the figure first to understand the basics of the graphics that it contains before addressing the question tasks. So within that 2-minute period, you don't want to look at the question first, look at the figure first. Figure out what they're telling you, figure out what information is presented so that you understand that before getting influenced by the specific question and potentially getting sidetracked. So you'll always want to assume these figures are drawn to scale, and you can approximate as appropriate. So if you see that it's 1/4 of a pie chart, that is a 90-degree angle and 25% of the whole thing. You don't have to second guess it. And you will want to engage with the interface calculator to help with any clumsy or complex arithmetic. Remember that the integrated reasoning section knows that you have a calculator. So if you're looking at some relatively complex or at least time-intensive calculations, remember to pop out the interface calculator because you do not have to manually calculate what 67% of 1.37847 is. So let's take a look at a sample information graphic. So on the left here, we've got a figure, and you'll always want to note what you've got, the titles, the variables, the legends, the axes, the metrics, and any possible trends. So here we see that we've got the acreage in hectares of farmland in India by source of irrigation from 1980 through 2008. And we see that that's what's represented here. We can see that on the left-hand side, we've got our million hectares from 0 to 70, and we've got all of the years from 1980 through 2008 on the horizontal axis. And then we have 4 different variables. We've got other in purple, which is the top. We've got wells in green, which is the second from the top. We've got tanks, which is in kind of a burgundy maroon color, in the second from the bottom, and then the absolute bottom is the blue canals. So you do want to always skim the accompanying text to determine if new information is provided, but you can see I really didn't need to do all that much with the accompanying text there. Your questions are generally going to be presented as blind drop-down menus for graphics interpretation questions. So this means that you kind of want to have an idea of what the correct answer should be before even having to look at those answer choices. So try to proactively determine the answer to whatever the question is asking to avoid needing to scan those hidden options. Now, here are a couple of sample questions. So our first one here is just asking, what is the source with the greatest percentage increase in irrigated hectares from 2000 to 2008? So we have to just make sure we don't cut corners, right? So we know we're not being asked about the entire duration of the time period represented in the graphic. So do not come over and start at 1980. That is going to be how you'll get the wrong answer. Instead, come just to 2000 here and look specifically at what has the greatest increase from a percentage perspective from that period to the end of the graphic at 2008. So we can see that in the purple at 2000, it's pretty small. It's actually gone down a little bit, and then it almost doubles in size. So that might be our correct answer. The green doesn't change a whole heck of a lot from 2000 to 2008. So even though it's the biggest proportion of the figure, the wells are not going to be the right answer here because they just don't have a great percentage increase. The tanks actually look like they decrease, and the wells look like they go pretty static. So Because it's percentage increase, we find out to learn that it's going to be the purple at the top, because it goes from a, kind of like maybe a 5 million chunk to what looks like almost 10 million chunk, or like 8 million chunk from that specific period. So just be careful. And you can see we don't even really have to engage with the calculator or calculations at all. We can eyeball this. We just have to make sure that we're eyeballing the right things, not going back to 1980 and accidentally potentially grabbing the green, or looking at something and not being careful enough. So then let's take a look at one more example question. We've got, over the 28 years covered by the figure, the percentage of India's irrigated area sourced water by canals has experienced closest to what percent change? So we've got a percent increase, a no change, a percent decrease, and a percent decrease. So again, on the exam, these answer choices wouldn't necessarily be revealed immediately. Instead, you probably just want to go do this work yourself up front. So we know that the canals are the blue at the bottom. And we can see that the canals are roughly 15 out of an original, say, 38 on the left-hand side. And then over time, we get around a 15 out of 63 on the right-hand side, if we go all the way up to where the purple is at the very top of 2008. So then it's just a matter of processing the percent change using the calculator. So we find that 15 out of 38 is about 40%. And that 15 out of 63 is about 24%. You apply the percent change formula using the calculator to find that 16 as the percent change, or the actual difference in the values rather, out of 40 is going to be about a 40% decrease. And there's our correct answer of choice D. So again, not complex, but rife with opportunities to make a mistake unnecessarily. So go through these carefully and you'll get them right. They shouldn't be overly complex. So let's take a look now at a more unique style graphic. You'll sometimes see things like this, sort of a flow chart. So you always want to calmly address the figure. Don't go, what is this? I have no idea what it is. You're going to be able to figure it out. You'll want to read the accompanying text, however, closely to understand the figure before moving to address the question. So we can see we've got a figure. There's 16 transistors. They're represented by triangles with the letters V, W, X, Y, and Z, denoting what are known as primary transistors. And the 4 power stations represented by the squares provide the sufficient electricity for all 16 of the transistors. Simple enough. We find that beginning from the power stations, each transistor transmits current in the direction of the arrows listed and loses half of the prior amperage in the transition of the current. Okay, so something's lost. So then the blank primary transistor is going to receive exactly 4 times the current received by which other primary transistor. So write out the figure to model the flowcharts as needed. So for instance, we can plug an easy value in to the model to model the movement of the chart. So if the amperage primary transistor W were 128, then the next would be 64, the following would be 32, primary transistor Z would be 16, the next would be 8, and primary transistor X would be 4 to satisfy the conditions of the problem. So just to sum up everything that we've done. First, carefully address the figure. Note all aspects proactively for information or unique graphics. Then, read and identify the question task. So, note the specifically sought value or values for each task, and beware of mistaking the details. Because again, these questions, they're not necessarily hard, but they're just chock full of traps. You'll then need to get the necessary info from the figure proactively. Logically estimate, though, as warranted. As we saw with our sample information graphic about the water sources, you didn't really have to engage with the calculator for both of those questions. And then confirm your answer. So use the interface provided calculator to guarantee accuracy. You have no reason to do the math from the graphics interpretation questions on the integrated reasoning section. Mentally use their calculator and double check your question and your selection to make sure you made no simple mistakes. Again, these ones are the ones that you should be able to get correct more reasonably in the section. Get your points from these questions so that you don't have to worry so much about some of the harder and more time-consuming two-part analysis and multi-source reasoning questions. So, That is our approach for the integrated reasoning graphics interpretation question type. Go ahead into the practice questions to attempt some drills of this question type on your own to improve your processes on this part of the exam.